Okay. So the next concept which we are studying is direction of chemical reaction at equilibrium. Okay. So what is meant by equilibrium we have studied in the last class. Nama? Evari va papers. Chinchasta sound asta. Sound rakodu. So Sima. So what is meant by equilibrium we have studied, no? So change in Gibbs free energy, it will be 0. Clear, Nama? Concentration of reactants and concentration of products, they will be constant. Concentrations may be equal, may not be equal. That is a different condition, but concentrations remain to be same. And rate of reaction also remains to be same. These are the conditions we have discussed now for equilibrium. Now we are discussing about direction of chemical reaction. Chemical reaction at equilibrium, it may be forward reaction also, it may be backward reaction also. That direction we need to find out. Are you able to understand, ma? So write down. So therefore, chemical reaction, okay, can be forward also or backwards also. Okay. So we study 3 parameters to find the direction of chemical reaction. Are you able to understand, ma? Okay, ma? So we study 3 parameters to find out the direction of chemical reaction, ma. First one is we will study about quotient ratio. Okay. We study about Gibbs free energy. Okay. And by using the third one, which is called as Lechatlier'S principle also, okay, ma, we try to find out the direction of chemical reaction. Are you able to understand, ma? So by using, we have to study these 3 parameters by which we can study what is the direction of the chemical reaction, whether it is forward direction or whether it is in backwards direction. So first one we have to study about is quotient ratio. Okay, ma? So what is meant by quotient ratio? Let us try to understand by taking an example. Okay. So for example, so N1A converts into N2B. This is the reaction. So what is meant by N1A converting into N2B, ma? So N1 moles of reactant A, it is converting into N2 moles of reactant B. Are you able to understand? So therefore, what is meant by quotient ratio here? Quotient ratio is nothing but, clear, ma? So the concentration of products to the power of N2 divided by concentration of reactants to the power of N1. This is called as quotient ratio. Okay? QC. When you look at this one, do you remember anything? So similar type of ratio we have studied previously. What was that? Equilibrium constant. Equilibrium constant also we studied same, no, ma? So the concentration of products to the power of its stoichiometric coefficient divided by the concentration of reactants to the power of stoichiometric coefficients. This is what we have studied, no? No, see. So first make a note up to here. Okay. Now let us try to understand this quotient ratio, ma? See here, what is the reaction we have taken? N1A converting into N2B. This is the reaction which I have taken, ma? So already we have studied, always we take 2 conditions. No? What are the 2 conditions we will take? First condition is at time is equal to 0. That is when chemical reaction is about to start. That time is called as T is equal to 0. So in that condition, let us consider there are A moles of reactant A. Then how many moles of product will be there, ma? 0 moles of product will be present. Are you able to understand? So therefore I will say at equilibrium, second condition. At equilibrium, how I have to write the reaction? I have to write it is A minus N1 into X. This is how I have to write, no? Because N1 moles, so finally it is converting into N2 moles. So how many moles of reactant will disintegrate? N1 moles will disintegrate. And how many moles of product will form? N2 moles of product will form. Are you able to understand? So therefore, how I have to write? I have to write N2 multiplied by X. So this is the condition which will happen at equilibrium. And after equilibrium also reaction will continue, no ma? So therefore, after equilibrium, how can I write? After equilibrium, I can write A minus N1Y, and here I can write N2Y. So after equilibrium, N1Y moles of reactant has disintegrated, and N2Y moles of product has formed. This is what will happen, no? Do you remember this process? Are you able to understand, ma? Okay. Now here, at T is equal to 0, how can I write a quotient ratio? Same. So concentration of products to its stoichiometric coefficient divided by concentration of reactants to the power of its stoichiometric coefficient. Are you able to understand, ma? At equilibrium also I have to write same, no? Divided by concentration of reactants to the power of N1. Similarly, after equilibrium also I have to write the same thing. So concentration of products to the power of its stoichiometric coefficient divided by concentration of reactants to its power of stoichiometric coefficient. Are you able to understand, ma? So therefore, this is a general principle, ma. This is a general term. Quotient ratio is called as a general term. And that general term at equilibrium, what you call, this one you can call it as K equilibrium. That's what we have studied, no? K equilibrium means what? It is also same ratio. The concentration of products to the power of its stoichiometric coefficient divided by concentration of reactants to its stoichiometric coefficient. So this is also QC, this is also QC, this is also QC. But this QC at equilibrium, it is also called as K equilibrium. And K equilibrium we define in how many methods? We define in two methods, no? Kp and Kc. What is Kc? Equilibrium constant in terms of molar concentration. And what is Kp? Equilibrium constant in terms of partial pressures. Are you able to understand, Amma? So this Kq can be, it can be either Kp or Kc. Are you able to understand what is happening? This already we have studied. But this is called Kq only at equilibrium. And at other conditions, if you take the ratio of concentrations, it is called as QC, quotient ratio. Are you able to understand? So therefore, what is the note point here? We are supposed to understand. Note point is that QC is a general term. QC is a general term. But at equilibrium, QC is called what? QC is called K equilibrium, equilibrium constant. Are you able to understand what is happening? That's it. So now, okay, ma? So I will write a relation between Gibbs free energy and standard Gibbs free energy, ma. Okay? So we study a relation between change in Gibbs free energy, okay, ma? And standard Gibbs free energy. Okay. So what is meant by standard Gibbs free energy, ma? Standard Gibbs free energy means what? Already we studied, no? Gibbs free energy at a particular temperature and at a particular pressure is called as standard Gibbs free energy. What should be the temperature? Temperature should be 25 degrees Celsius. And what should be the pressure? Pressure should be 1 atmospheric pressure. Already we have defined, no? So at that pressure and at that temperature, the Gibbs free energy is called as standard Gibbs free energy. Okay? So the relation between them is like this. So we will write Gibbs free energy is equals to standard Gibbs free energy plus 2.303 RT log QC to the base 10. Okay, ma? This is the relation between Gibbs free energy and standard Gibbs free energy. Are you able to understand? So delta G is equals to delta G standard plus 2.303 RT log QC to the base of 10. Okay, now see. So at equilibrium, what happens to standard Gibbs free energy, ma? What happens to Gibbs free energy? It becomes 0. Already we have studied, no? Or we can say only when delta G will become 0, then only reaction will be in equilibrium. Already we have studied, no? So that condition we are taking. At equilibrium, delta G will become 0. Okay, ma? Standard Gibbs free energy may become 0, may not become 0. But this one is always 0 at equilibrium. Gibbs free energy is always 0 at equilibrium. Standard Gibbs free energy, it may be 0, it may not be 0. Okay? So if this value is 0, then what happens to the remaining value? I can write a 0 is equals to standard Gibbs free energy plus 2.303 RT log QC to the base of 10. This is how I can write now. Are you able to understand? Now take this 2.303 to the other side, then I can write delta G standard is equals to minus 2.303 RT log QC to the base of 10. I can write like this. Understood now? Now see. So we are studying this at which condition? We are studying this one at equilibrium. No? At equilibrium, QC can become K equivalent. No? Are you able to understand? At QC, at equilibrium, this quotient ratio is nothing but equilibrium constant. And equilibrium constant can be Kc also, it can be Kp also. Are you able to understand? So therefore, instead of Kc, if I write Kp, nothing will happen. No? So therefore, how can I change this equation is like this. Okay, ma? So this equation again I will write like this. Okay. So standard Gibbs free energy is equals to, I can write like this, log P log Kp to the base 10. Why I am writing like this? Because since at equilibrium QC is nothing but Kp. Is it clear, ma? So this is the relation which I got at which condition? At equilibrium. Are you able to understand? Now here we will write some cases, ma. Are you following very carefully, ma? Because if you miss at least one step, then I don't think you are going to understand this one. Clear? This is a sequential process, no? So listen very carefully. Now we write some cases, ma. Case number 1 is if Kp will become 1. Okay, ma? So equilibrium constant, if it becomes equal to 1, then what does this value become? This becomes log 1 to the base 10, no? If Kp becomes 1, then this is the value which I get, no? Log 1 to the base of 10. And what is log 1 to the base 110? Mathematics you did not study? It will be equal to 0. Are you able to understand, ma? Log 1 to the base 10 will be how much? It will be 0. So 0 multiplied by 2.303? 0. So therefore, standard Gibbs free energy also will become 0. Are you able to understand? Therefore, what I can write? Standard Gibbs free energy also will become 0. So standard Gibbs free energy is becoming 0 at which condition? Only when Kp value if it is 1. And what is meant by Kp already we have studied, no? What is Kp? Kp is nothing but partial pressures of products to the power of its stoichiometric coefficients divided by the partial pressures of reactants to the power stoichiometric coefficients power. This is Kp, no, ma? It means if concentrations, partial pressures, if they are equal, okay, then Kp will become equal to 1. If Kp equals to 1, then standard Gibbs free energy also will become 0. This is my case number 1. Are you able to understand? Now let us take one more case. Case number 2. So what can I write about case number 2? Clear, ma? So if Kp is greater than 1, or you can say Kp is positive. Okay, ma? If Kp value is positive. So if Kp value is greater than 1 or when it is positive, then log Kp to the base 10 also will become positive, no? Okay, ma? Positive multiplied by negative value? Negative. So therefore standard Gibbs free energy will become negative. So therefore I will write standard Gibbs free energy will be negative, or I can say standard Gibbs free energy will be less than 1. This is what I can write. Are you able to understand? So if Kp is greater than 1, then what about standard Gibbs free energy? It will be less than 1 at equilibrium. Are you able to understand, ma? Okay. So all these cases you should remember, ma, because direct questions were asked many times previously on the same topics. Clear? Next we will write case number 3. Okay. Now what can be case number 3, ma? If Kp is less than 1, or you can say if Kp is negative. If Kp is negative value, then what will happen? Okay, see, ma. So log Kp to the base 10 also will become negative, no? Negative multiplied by negative? Positive. So standard Gibbs free energy will become positive. Are you able to understand? Therefore I can say standard Gibbs free energy is positive, or you can say standard Gibbs free energy is greater than 1. So these are some of the conditions which we have to remember in the terms of standard Gibbs free energy. Are you able to understand, ma? Okay. Now actually, what was the relation we have written, ma? Relation between Gibbs free energy and standard Gibbs free energy was what? Clear? So delta G is equals to delta G standard plus 2.303 RT log QC. This was the relation which we have written, ma? Now do one thing, take this value and substitute here. Okay? If I substitute, what I will get? Standard Gibbs free energy is equals to minus 2.303 RT log Kp plus 2.303 RT log QC. This is what I will get, no? Now what are the terms which are constant here? 2.303 RT is constant, no? Take it outside. So therefore, Gibbs free energy is equals to 2.303 RT. Now first I will write a positive value, ma. So log QC minus log Kp. So log A minus log B? Log A by B. Clear, no? So substitute. So therefore Gibbs free energy can also be written as 2.303 RT log QC divided by Kp. So this is another very important relation which we got. Are you able to understand, ma? Are you able to understand what is happening? This was the relation which we studied previously, no, ma? Now we got one equation for standard Gibbs free energy, no? That relation we are substituting in the original equation. Then I got one more equation. Is it clear? Okay. Now to this equation, again we will write some cases, and these cases are very important. Clear? Completed up to here? Now see. Now let us see what are the cases we can write. Okay? So again we are going to write some cases. Okay, ma? See, ma, first case, at equilibrium, what happens to Gibbs free energy? 0, no? So delta G will become 0. Okay? If delta G becomes 0, this total terms also will become 0, no, ma? If they become 0, then QC and QP, they should be equal to each other, no? Why? Because QC divided by QP, if it is 1, then only log 1 to the base 10 will become 0. Are you able to understand? See, ma. If this value is 0, then I have to write log QC divided by Kp to the base 10 also should become 0, no? This will become 0 in which condition? Only when QC and Kp when they are equal. So therefore, QC must be equal to Kp. So this is one observation. Okay? Now when Gibbs free energy is 0, then there is no direction for this equilibrium reaction. No direction. It is not traveling in forward direction also. It is not traveling in backward direction also. So therefore here chemical reaction does not have any direction. Does not have any direction. Are you able to understand, ma? Now we will write case number 2. Case number 2 is Gibbs free energy if it is less than 0, or you can write when Gibbs free energy is negative. Okay, ma? When Gibbs free energy is negative, then the reaction will be always in forward direction. Are you able to understand? When Gibbs free energy is less than 0, or it means that if it is negative, then what is the direction of reaction? Reaction is always in forward direction. So write down. So then we can say reaction is in forward direction. Clear? Reaction is in forward direction. Now you observe this relation. Now can you say what is the relation between QC and Kp, ma? QC is greater than Kp, less than Kp, equal to Kp. Come on. See, ma, if delta G is less than 0, then 2.303 RT log QC by Kp also should be less than 0, no? If it is less than 0, it is possible only when log QC by Kp is less than 0. Log QC by Kp is less than 0 only when QC is less than Qp. Understandable only, no? Are you able to understand, ma? Therefore, what I can say? We are not discussing about delta G if it is 0. Delta G 0 already we have discussed, no? Here reaction is in equilibrium. That is standard Gibbs free energy. We are not discussing about standard Gibbs free energy. Standard Gibbs free energy already we have substituted. Are you able to understand, ma? We are discussing about what? We are discussing only about Gibbs free energy. We are not discussing about standard Gibbs free energy. That already equation lo substitute chesesnam kada manam. అర్థం కాలేదు సీక్వెన్స్ ఎలా చేస్తున్నాము. దిస్ ఆల్రెడీ వీ హ్యావ్ డిరైవ్డ్ వన్ ఈక్వేషన్ అండ్ అగైన్ వీ హ్యావ్ సబ్స్టిట్యూటెడ్ ఇన్ ద సేమ్ ఈక్వేషన్. Are able to understand ma? Now we are studying only about Gibbs free energy. We are not discussing about standard Gibbs free energy. This is the equation. Are able to understand? Now see ma. So therefore, if Gibbs free energy is less than 0, it means it is negative. Then what is the meaning of this one? Therefore, log to the base 10 QC divided by KP also should be less than 0. Okay? And it is possible in which condition ma? It is possible only when QC is less than KP. That is the condition. Are able to understand? So therefore, when reaction is in forward direction, then QC will be always less than KP. Direct questions were asked previously on this relation. Are able to understand ma? Okay. Now case number 3. Now can you say what can be case number 3 ma? So Gibbs free energy is greater than 0. If Gibbs free energy is greater than 0, then log QC divided by KP also should be greater than 0. And it is possible only when QC is greater than KP. That's it. Okay ma? Therefore what I can say, log QC divided by KP must be greater than 0 and it is possible only when QC is greater than KP. Are you able to understand? And when this when this Gibbs free energy is greater than 0, then the reaction is always in backward direction. Okay ma? When Gibbs free energy, when it is 0, greater than 0, then reaction is always in backward direction. So this is one more point we should write down. So reaction is in which direction? Reaction is in backward direction. Understood nama? So therefore the values of delta G, the values of QC and the value of QP, they decide the direction of the reaction. Are you able to understand ma? Whether reaction is in forward direction, whether reaction is in backward direction, or at equilibrium there is no direction for the reaction. Okay? When Gibbs free energy, when it is 0, where is that? Then the reaction doesn't have any direction. Okay ma? When it is less than 0, then in previous topics we have studied reaction will be instantaneous also, no? When Gibbs free energy, when it is less than 0 or when it is negative, are you able to understand ma? Reaction will be spontaneous also. And reaction will be in forward direction also. Are you able to understand? And what is the last statement? When Gibbs free energy, when it is greater than 0 or when it is positive, okay ma? Then the reaction is always in backward direction and QC will be always greater than KP. Understood now? That's it. Make a note up to here. Okay ma? So for example, if this is the given question ma, so QC value for the reaction, this is the reaction ma. Then already we have studied nama, what is meant by QC? The concentration of products to the power of its stoichiometric coefficient divided by the concentration of reactants to the power of its stoichiometric coefficients. So the reaction will proceed towards the right side in which of these cases? What is meant by right side? Right side is nothing but forward reaction. Are you able to understand ma? So in which condition it will proceed in forward direction ma? Already we have studied, no? Quotient ratio should be less than equilibrium constant. QC is less than QC. Only in this condition, I can say this reaction will proceed towards right side or in forward direction. Okay ma? So write down. So right side means what? Right side is nothing but in forward direction. Are you able to understand ma? Therefore we say, so QC is always less than KC. Only in this condition the reaction will be in forward direction. Understood now? That's it. Okay ma? See ma. So the next concept which we are studying is vapor density ma. So previously in some topic we have written a relation between molecular weight and vapor density. Do you remember? When studying Graham's law of diffusion, we studied this one ma. So what is that? Okay. So molecular weight of a gas is equals to 2 times its vapor density. Do you remember this one? Molecular weight is 2 times of vapor density of a gas. Are you able to understand ma? So therefore what is vapor density? Vapor density is equals to molecular weight divided by 2. So this is a relation. Are you able to understand? For example, if I take a relation, A converts into NB. Consider this is a relation. Okay ma? So again I will write at T is equal to 0. Okay ma? So let us consider 1 mole of reactant was present. Then how many moles of product will be there ma? 0 moles of product will be present. Are you able to understand? Then at equilibrium, let us consider x moles of A has disintegrated. X may be anything, 1 by 2, 1 by 4, anything. Okay, ma? Then how many moles of product will form, ma? N into x moles of product will form, no? Do you remember? Because basically that is the reaction which I have taken, no, ma? If 1 mole disintegrates, then n moles of product will form. Similarly, if x moles disintegrates, then n into x moles of product will form. Are you able to understand? Okay. Now at t is equal to 0, that is before the starting of this reaction, vapor density is represented by capital D. Are you able to understand? That is before the starting of reaction, vapor density will be different. Because products and reactants, they are not the same, no, ma? Products will have a different vapor density, reactants will have a different vapor density. Because number of moles formed will be different. Are you able to understand, ma? Now see. So therefore, vapor density is called capital D at which condition? At the starting of the reaction. That is when T is equal to 0. Okay. Then at equilibrium, here vapor density, I will represent it as small d. Are you able to understand? Okay. Now at T is equal to 0, reactants were present or products were present or both were present? At T is equal to 0, only reactants were present, no? Are you able to understand, ma? So therefore, vapor density, how I can write? D can be written as molecular weight of reactants divided by 2. This is how I can write, no? Are you able to understand, ma, what is happening? At T is equal to 0, only reactants will be present. Still reaction has not started, no? So only reactants will be present. So therefore, molecular weight I have to take of what? Molecular weight of reactants only divided by 2. Are you able to understand? Okay. Now at equilibrium, what is happening? At equilibrium, some reactants is also present, some moles of products are also present. So 1 minus x moles of reactants is present, nx moles of product is also present. That is what is happening at equilibrium, no? So therefore, what I will do is, here vapor density small d. Vapor density small d is equals to molecular weight of mixture of gases divided by 2. This is the method which we have to use. Okay, ma? We have to take the molecular weight of mixture. Mixture means what? Reactants are also present, products are also present. All the reaction is happening in same container only, no? Reaction is happening in same container only, no, ma? Some products also will be there, some reactants also will be there in gaseous form. Are you able to understand? The vapor density is only for gaseous form only, no? Sometimes he will ask questions like this also, ma? A solid will be given, from solid gas will be formed. Then what is the vapor density? There is no vapor density because solid is present, no? We are discussing only in gaseous forms only. Vapor density will be only because of gases only. They will not be because of solids. Are you able to understand? So see. So therefore, at the starting of reaction, I will write molecular weight divided by 2. And molecular weight I will take for reactants because only reactants will be present. But at equilibrium, some reactants also will be there, some products also will be there. So in that condition, vapor density, how I can write? Molecular weight of the mixture of gases divided by 2. This is the method which I have to use. Are you able to understand? So right now. So after this, there is one more very important relation which we need to remember, ma. Clear, ma? That is relation between degree of dissociation and vapor density. Okay, ma? Vapor density. Okay. What is meant by degree of dissociation, ma? Do you remember? Or fraction of dissociation. Degree of dissociation is also called what? Fraction of dissociation. Do you remember? Okay. It is called alpha, no? Alpha. What is alpha? X divided by A. This is alpha, no? X is the number of moles of reactants which have disintegrated. And A is the initial number of moles. Gurtunnai kada ivi? Okay, ma? So I want to have a relation between alpha and this vapor density. Okay? And the relation is written like this. So D minus D divided by N minus 1 multiplied by D. This is the relation. Capital D minus small d divided by N minus 1 multiplied by small d. Are you able to understand? So what is meant by capital D, ma? Capital D means what? Vapor density where? At T is equal to 0. Clear, no? Small d? Vapor density at equilibrium. Are you able to understand? And here N is not number of moles, ma. This is number of moles of products when compared to 1 mole of reactant. Are you able to understand? So write down the definition of N here. What is meant by N here? N is number of moles of product formed per 1 mole of reactant. Are you able to understand, ma? N is not total number of moles, ma. N is not total number of moles. What is N? How many moles of product is formed for 1 mole of reactant? For every 1 mole of reactant, how many moles of product is formed? That is called as N value. Are you able to understand? So remember that one very carefully. Okay? Or we can write one more relation like this also, ma. How I can write? So vapor density at initial condition divided by vapor density at equilibrium, this is equals to number of moles of gaseous mixture at equilibrium divided by number of moles at initial condition. Okay, ma? So this is also a very important relation, ma, which you can remember. Sometimes questions can be asked directly on this relation. Are you able to understand? So therefore, vapor density initial divided by vapor density at equilibrium. Okay? This is equal, see, ma, here I have initial, no? But here in the denominator I should have initial. Equilibrium is in denominator, no? So gaseous mixture should be in numerator. So this relation you can remember. Are you able to understand? So VD initial is also called as capital D, no? Initial vapor density. Vapor density at equilibrium is also called small d. Okay? So you can write like this also. Okay? For example, if I write any reaction, so let us consider A converts into NB. Let us consider this is a reversible reaction. Are you able to understand, ma? So listen very carefully. So at T is equal to 0, let us consider 1 mole of reactant was present. 1 mole of reactant was present. So how many moles of product will be there? 0, because reaction still has not started, no? Are you able to understand, ma? Now at equilibrium, okay, I have to write 1 minus X. Okay? X amount of moles of reactant has disintegrated. Then how many moles of product will form? N into X. Nx moles of product will form. Okay, now see. Now we will try to fill this equation which we have written here. Now see, ma. So number of moles of gaseous mixture at equilibrium. What is meant by gaseous mixture? Number of moles of reactants and number of moles of products. Reaction is happening in a container only, no, ma? In container, products also will be there, reactants also will be there. So you take the number of moles of reactants also, products also, that is called as number of moles of gaseous mixture. Okay? Now can you say how many moles of gaseous mixture is present at equilibrium, ma? 1 minus X plus N into X, that's all, no? So write it. So therefore I will write 1 minus X plus N into X divided by, so number of moles initial. Initially only reactant was there, no, ma? And how many moles of reactant was present initially? Only 1, so divided by 1. Are you able to understand? Now let us see if I can simplify this one. So I can write 1 minus X plus Nx divided by 1. X I can take common, no, ma? So 1 plus, if I take X common, then it is N minus 1 divided by 1. So you can write like this also, capital D divided by small d. This is one more equation for vapor density initial divided by vapor density at equilibrium. Are you able to understand, ma? So this is one example I have taken, ma. You can take any example and you can always use this relation. Are you able to understand? Make a note of it. ఆలోచించడమా ఈ పెద్ద కామెడీ ఇది. Okay, ma. So see here. So see, my vapor density of PCl5 is 104.16 my initially, and when heated to 230 degrees Celsius, its vapor density has become 62. So therefore, let us see what is the data given. First of all, capital D he gave nama 104.16 before the starting of the reaction. Okay, and small d also he gave, no, after this reaction started, then D value is only 62 at equilibrium. Are you able to understand? Then the degree of dissociation is how much? Degree of dissociation means what? Alpha value, no? Alpha value is nothing but degree of dissociation. But he did not give fraction, ma. He gave in terms of percentage. It means alpha multiplied by 100. This one we are supposed to calculate. Are you able to understand? Alpha is just a fraction, no? X by A. Alpha multiplied by 100 will give percentage. And option is given in terms of percentages only. Okay. So what is alpha value? Alpha value can be written as X divided by A. Or we can write capital D minus small d divided by n minus 1 multiplied by small d. Like this also I can write, Nama. Now see, capital D we know, small d also we know, just n value I don't know. So for that we need to understand what happens if this PCl5 is heated. Okay. So PCl5, when it is heated, it converts into PCl3 plus Cl2. So this is the reaction which is happening when you heat this PCl5. Are you able to understand, ma? Now see. So here initially, how many moles of PCl5 was present? 1 mole. Here n value is 1. Clear, no, ma? And how many moles of reactants are formed? Sorry, how many moles of products are formed? 2 moles of products are formed. So here also I have n is equal to 1, no? PCl3 also 1 mole is forming, and Cl2 also 1 mole is forming. Are you able to understand? Now, what is meant by this n value, ma? Do you remember? N, did I say, is it equal to number of moles? No. What is n? N is the number of moles of products when compared to 1 mole of reactant. Here I have taken only 1 mole, no? So when compared to 1 mole of PCl5, how many moles of reactants have formed? 2 moles of products have formed. So therefore here I can definitely say that n value is 2. Are you able to understand? Clear? Now do the calculation. Okay, ma? So therefore just substituting all the values. So alpha value is how much? So capital D 104.16, small d 62 divided by n minus 1, 2 minus 1 multiplied by small d. Small d value is again 62. So alpha value if you do, it will get 0.68. This is the answer which you will get. But I want percentage, no? So therefore what I will do, alpha multiplied by 100 is how much? 68%. So that is our answer. 68% should be our answer. Clear, ma? That's it. Okay. So see, my next concept which we are discussing is Lechatlier'S principle, also called as Brown principle. Clear, no? So this is a very interesting discussion, no? So once you understand this one, solving of problems also will be very easy. Okay. So I will explain the concept of this one, then I will give you some problems. You have to do the problems. Okay. So see. So what is this principle saying? See, in a chemical reaction at equilibrium, so if concentration, pressure or temperature when they change, clear, no? Then equilibrium will shift in that direction such that this effect is cancelled or this effect is nullified. This is called as Lechatlier'S principle. Are you able to understand, no? So for example, if I say that if concentration is increasing, either products or reactants, then equilibrium will shift in that direction such that that concentration is again reduced. Are you able to understand? Similarly, if concentration is reducing, then equilibrium will shift in that direction such that concentration will reduce. Okay? It means we have to do opposite work. Are you able to understand, no? So therefore, what is the point by which we understand this one? Okay, ma? So, equilibrium shifts in opposite direction. Just if you remember this point, very easily we can understand what is happening. Are you able to understand? So, it means we have to do opposite work, ma, that's it. Okay? Let us try to understand by taking some examples. Okay? So, first of all, we will study effect of concentration. Okay, ma? So what is happening to the concentration of reactants, what is happening to the concentration of products, that we will study. Okay, now see. So first of all, let us take case number 1. Okay, ma? So concentration of products is increasing. Are you able to understand, ma? So this is the case given. Okay, concentration of products is increasing. Okay. Now equilibrium should shift in which direction? Equilibrium should shift in a forward direction, or equilibrium should it shift in backwards direction? That I want to find out. Are you able to understand? Now see, ma. So if concentration of products, if it is increasing, reaction is undergoing forward reaction or backward reaction? Forward reaction.
So reaction is in forward direction. Then only the concentration of products will increase. Are you able to understand? For example, if I write N1A converts into N2B. So here which is the reactant and which is the product here? So this one is the reactant, okay, and this is the product. What is the meaning of this one, Nama? So if concentration of product is increasing, okay, then it means that reaction is in forward direction. Okay, that point I can understand. No? So therefore, a reaction is in which direction? Reaction is in forward direction. Okay, ma? Then equilibrium should shift in which direction? Backwards direction. Are you able to understand? No? That's what we have written here. No? Equilibrium will shift in opposite direction such that the effect of that change that is cancelled. So here what is the change which is happening? Increasing of concentration of products. So how can I decrease the concentration of products? When reaction undergoes backward direction. Are you able to understand, Amma? So therefore what I say, therefore here, equilibrium shifts in which direction? Ma? Equilibrium shifts in backward direction. Okay. So equilibrium, if it shifts in backward direction, what happens to the concentration of products? Concentration of products will reduce. Because already we have studied, these are reversible reactions. No? So from reactants, products will form, and from products, reactants also will form. Okay. So this is one example. So I will write some more examples, try to say their conditions. Okay. So for every 2 exams, you will be getting 1 question from this one. Lechatlier'S principle. Okay. Case number 2. What is case number 2? Concentration of products is decreasing. Concentration of products is decreasing. Then reaction should shift in, equilibrium should shift in which direction? Forward direction. That's all. Just opposite of this one. Okay. So if concentration of products is decreasing, it means the reaction is undergoing which direction? Reaction is happening in backward direction. Okay. So therefore equilibrium should shift in forward direction. That's it. Okay, ma? Therefore, reaction is in backward direction. Okay. So therefore equilibrium should shift in opposite direction. No? So therefore it will shift in forward direction. That's it. Very simple. And similarly you can write case number 3 and case number 4 also. No? What is case number 3? Case number 3 is concentration of reactants. Concentration of reactants is decreasing. Okay, ma? So if concentration of reactants is decreasing, okay, then the reaction is in forward direction or backward direction? Forward direction. So equilibrium should shift in backwards direction. So therefore, equilibrium shifts in backward direction. So are you able to understand now what is happening? Now we can write case number 4 also. No? What is case number 4? So concentration of reactants is, what is happening? Is increasing. Okay, ma? So if concentration of reactants is increasing, it means reaction is going in which direction? Reactants, if they are increasing, then reaction is happening in backward direction. So equilibrium should shift in forward direction. That's all. So answer is forward direction. That's it. Understood, Nama? So this is the effect of concentration. So for the direction in which the equilibrium should shift. That's it. Very simple. Is it clear, ma? Okay, ma? So next one is what is the effect of concentration on equilibrium constant? Equilibrium constant already we have studied, no? K value. K equilibrium, KPR, KC. 2 types of equilibriums we have studied, no? Equilibrium with respect to molar concentration, equilibrium with respect to partial pressures. Okay. So if concentration changes, what is the effect of concentration on equilibrium constant? Can you say anybody? Already discussed cheskunnam. In the previous 2 days before, I think we have discussed this. So what is the effect of concentration on equilibrium constant? Equilibrium constant depends on how many factors? Two factors. What are they? One is temperature and the second one is stoichiometric coefficients. This is what we have studied, no? Okay, ma? So what is the effect of concentration on equilibrium constant? No effect. Whatever may be the change in concentration, equilibrium constant will never change. This is the point which you should remember. Okay, so write down. So therefore, no effect. No effect of concentration on equilibrium constant, because equilibrium constant depends only on two factors only. One is temperature and the second one is stoichiometric coefficients. That's what we have discussed, no? Okay, ma? So then we study the second one, which is called as effect of temperature on direction of equilibrium. Okay, ma? This is the second one. First one is effect of concentration, no, ma? And what happens to the concentration, that already we have studied. And depending on concentration, K value does not change. Okay. Second application which we are studying is effect of temperature on the direction of equilibrium shifting. Are you able to understand, ma? So here also we will study two cases, ma. Okay. Case number one. Case number one is reaction is endothermic reaction. Okay, ma? Reaction is endothermic reaction. So what is meant by endothermic reaction, ma? It absorbs heat energy. That is, for this operation to be done, for this reaction to happen, we have to supply heat energy. That is called as endothermic reaction, no? So delta H, will it be positive or negative or zero? Change in enthalpy, will it be positive or negative or zero? Positive. Why it is positive? Because in chemistry already we have studied previously, no, ma? Anything which enters into the system is taken positive, and anything which leaves the system is taken negative. Are you able to understand, no, ma? So therefore, change in enthalpy is considered positive because reaction is endothermic. Are you able to understand? Okay. Now here I will study two sub-cases, ma. Okay. Sub-case number one. Sub-case number one is temperature is increasing. Temperature is increasing. Are you able to understand? So, what is meant by temperature is increasing? Reaction, is it in forward direction or negative direction? Opposite direction, that you have to understand. Are you able to understand? So, here reaction is endothermic reaction. Okay? It means as the reaction process progresses, we have to supply heat energy. Okay, ma? It means what happens to the temperature of the system? Temperature of the system continuously reduces because it is absorbing heat energy. If it is releasing heat energy, temperature of the system will increase, no? If reaction is releasing heat energy, as reaction progresses in forward direction, what happens to the temperature? Temperature should increase because it is releasing heat energy. Okay? But in forward direction, if it is an endothermic reaction, are you able to understand, ma? So if reaction is undergoing forward reaction, what happens to the temperature? Temperature should decrease. But what is the case I am taking? Temperature is increasing. What do you understand? It means reaction is not going in a forward direction, it is going in backwards direction. That is the meaning of it. Are you able to understand? Okay, ma? Endothermic reaction means as the reaction progresses, it becomes cooler and cooler. Okay? Because it requires heat energy. It has the need to take the heat energy. And what is exothermic reaction? As the reaction progresses in forward direction, it releases heat energy. It means what happens to the temperature of the contents? They will increase. But here temperature of the contents will decrease in forward direction. But in backward direction, temperature will just do the opposite thing. It will increase. Okay? So here if temperature is increasing, so is it reaction is undergoing forward direction or backward direction? Backward direction. Then equilibrium should shift in forward direction. That's all very simple. Are you able to understand how to analyze this one? So right now. So in endothermic reaction, okay, ma? In forward direction, okay, temperature should decrease. Okay, but what is the case we have taken? But case is temperature is increasing. Understood, no? Temperature is increasing means reaction is in which direction? Therefore, reaction is in backward direction. Okay? Therefore, equilibrium should shift in? Therefore, equilibrium should shift in back forward direction. Okay, ma? So, if a particular change is happening, first you have to identify reaction is undergoing in which direction. Then equilibrium will shift exactly in opposite direction. We are supposed to do opposite work. That's it. That is the point which you should remember. Clear, no? Now, case number 2, can't you write now? Subcase number 2 you can write now. So, what is subcase number 2? Subcase number 2, just opposite of it. Okay? Temperature is decreasing. Temperature is decreasing. Okay, ma? So, if temperature is decreasing, what is the meaning of this? Reaction is forward or backward? In endothermic reaction, as the reaction progresses in forward direction, temperature reduces because it is absorbing heat energy. It utilizes the heat energy. So, temperature continuously reduces. Okay? So, reaction is in which direction? Reaction is in forward direction. Therefore, equilibrium should shift in which direction? Equilibrium shifts in backward direction. Understood, Nama? Okay. So, this is case number 1 which we have taken. Now, case number 2, can't you write? What is case number 2? So, reaction is exothermic reaction, and then can't you write again subcase number 1 and subcase number 2? Ma? Come on, write down. Okay, ma? So, case number 2. Case number 2 is reaction is exothermic reaction. Okay, ma? So, what is meant by exothermic reaction? It is releasing heat energy. As the reaction progresses, it releases heat energy. Releases heat energy means temperature of the system continuously increases. And because it is releasing heat energy is going out of the system now. So, anything goes out of the system is taken as negative in chemistry. Okay? So, delta H is negative. So, case number 1, subcase number 1, temperature is increasing. If temperature is increasing, it means that reaction is undergoing forward direction. So, reaction is in forward direction, so therefore equilibrium should shift in backward direction. So, case number 2, subcase number 2, temperature is decreasing. It means reaction is exactly undergoing backward direction. So, equilibrium should shift in forward direction. That's all very simple. Clear, no? Okay. So, now we will study what is the effect of temperature on equilibrium constant. Clear, no? So, already we studied that equilibrium constant depends on temperature, no? If temperature changes, equilibrium constant also will change. So, that we are going to see now. Completed, no? So, now on this discussion also questions were asked previously, no? So, let us see very carefully. So, effect of temperature on equilibrium constant. Okay. So, we have a relation. No? So, at temperature T1, let equilibrium constant be K1. Similarly, at a temperature T2, let equilibrium constant be K2. Okay. Then we have an equation like this. So, log K2 divided by K1. Okay, ma? So, this is equals to delta H divided by 2.303 R multiplied by 1 by T1 minus 1 by T2. This is the relation which we have. Are you able to understand, Amma? So, this is a relation which explains how K1 and K2 values they will change with respect to temperature. Okay? So, what is K1? This is the equilibrium constant at a temperature of T1. Understood, Amma? And what is K2? K2 is the equilibrium constant at a temperature of T2. Already we discussed that K value depends on temperature, Amma. So, if temperature changes, definitely K value also will change. Okay. Now, here again we have two cases now. Okay, already we discussed two cases, no? Delta H may be positive, delta H may be negative also. Are you able to understand? Similarly, temperature may increase and temperature may decrease also. Both cases are possible. Okay. Now, depending on how temperatures are increasing and whether delta H is positive or negative, we can decide whether K2 value is bigger when compared to K1 or K1 is bigger when compared to K2. If K2 is bigger, it means equilibrium constant is increasing. If K1 is less than K2, then it means, sorry, if K2 is less than K1, then it means that equilibrium constant value is decreasing. So, many cases we can study. Let us study some cases. Okay, ma? So, let us consider delta H to be positive. Let us consider. We will discuss some cases. My remaining cases I hope you can. Just if you observe the equation carefully, you can understand. So, let us consider delta H is positive. Clear? And let us consider T2 is greater than T1. T2 means final temperature. T1 means initial temperature. Final temperature is greater than initial temperature. It means temperature is increasing or decreasing? Temperature is increasing. Now, by using these two information, I have to check whether K2 is greater than K1 or K1 is greater than K2. Okay. Let us see how we can proceed in this condition. See, ma'am. So, T2 is greater, no? If T2 is greater, what about 1 by T2? T2 is bigger than T1. Then what about 1 by T2? 1 by T2 will be smaller than 1 by T1 because we are taking reciprocals. Are you able to understand? Let us see, for example, 10 is greater than 5. Do you agree? Correct only, no? Oh. Then what about 1 by 5 minus 1 by 10? What about this one? 1 by 5 is bigger when compared to 1 by 10. That's all, no? So, if you take general values, then one value will be bigger than other value. But if you take the reciprocal, so the values will exactly change. Are you able to understand, no? So, therefore, definitely I can say in this condition, 1 by T2 is less than 1 by T1. That's all, no? If T2 is greater than T1, 1 by T2 will be less than 1 by T1. Are you able to understand? So, if 1 by T2 is less than 1 by T1, 1 by T1 minus 1 by T2, will it be a positive value or negative value? Definitely positive value, no? 1 by T1 is bigger when compared to 1 by T2. Okay, so 5 minus 4 plus 1. So, I will get plus value, no? Positive value I will get. So, let us see. Okay. Now, listen very, very carefully. See now. So, definitely I can say 1 by T1 minus 1 by T2 is what kind of value? It is a positive value. That's all, no? And delta H is also taken positive. It means it is an endothermic reaction. Endothermic reaction only, no? Endothermic reaction. Okay. So, delta H is positive. 1 by T1 minus 1 by T2 is also positive. Then what about log K2 by K1? It also will be positive only, no? And it is possible only when K2 is bigger than K1. Are you able to understand, no? Therefore, log K2 divided by K1 is also positive. Okay. And it is possible in which condition? Only when K2 will be bigger than K1. So, this is the condition. Okay. So, here a temperature is increasing and it is an endothermic reaction. Then equilibrium constant is also increasing. So, this is the method of analyzing the equation. Are you able to understand? Ma? And now, whatever may be the question, whether delta H is positive or negative, whether temperature is increasing or decreasing, always you have to follow this method. Then you will understand whether equilibrium constant is increasing or decreasing. Is it clear, ma? Remaining cases, I hope you can do them, no? So, remaining 4 cases are there. Temperature decreases, one case. Delta H negative, in that again you will get 2 more cases. So, all those cases you can understand very easily if you analyze in this method. Are you able to understand, ma? So, therefore, what is the reaction here we have done? Here what we have done, ma? This is what kind of reaction? In endothermic reaction. In endothermic reaction. Temperature is increasing or decreasing? Temperature is increasing. If temperature increases, clear? What happens to K value? K value also increases. Understood, Nama? Is it clear? That's all very simple. So, first of all, delta H we are taking positive. and we are taking the condition that temperature is increasing, then we understood that K value is also increasing. Now exactly another statement you can write, if you take same endothermic reaction, if temperature decreases, K value also decreases. That's all. And what about exothermic reaction? Exactly opposite statements we have to write. Is it clear? That's it. Remaining no need of explaining Nama. I hope you can do that. కుదరదు ఈరోజు రాయండి ఓకేమా సో ఇన్ Lechatlier'S principle the third change is change in pressure. So what is the effect of pressure on the direction of equilibrium shifting? Okay, so let us try to understand this one by taking some examples. So see, so consider 2 moles of A, it is convertible into 3 moles of B. So consider this is a reaction. You're able to understand? No? What does 2 indicate here? Stoichiometric coefficient, no? So 2 moles of A will form 3 moles of B. Are you able to understand? Now here, if I write a case that pressure is increasing, okay, ma? Pressure is increasing. Now if pressure is increasing, can you say equilibrium will shift in which direction? Forward direction or backward direction? How can you say? We are not discussing about temperature. We are discussing about pressure here. See the reaction and see what is the change which is happening. Reactants are 2 moles. Products is 3 moles. What do you understand? Sima, if pressure is increasing, reaction is happening in which direction? Forward direction, because already we discussed that the ratio of number of moles and ratio of pressures, they remain same, no? If number of moles of gas increases, what happens to pressure? Pressure also increases. So if pressure is increasing, it means reaction is happening in forward direction. That is the meaning of this one, no? Because 2 moles, it is converting into 3 moles. Number of moles are increasing. Number of moles are increasing means number of molecules are increasing. If number of molecules are increasing, it means pressure automatically increases. Okay. So therefore, what I understand that reaction is in which direction? Reaction is in forward direction. Are you able to understand, ma? Because number of moles of product is greater. Okay. So pressure increases. Pressure increases. So reaction is in which direction? Reaction is in forward direction because number of moles are increasing. If number of moles increases, pressure automatically increases. So therefore equilibrium should shift in which direction? Equilibrium must shift in opposite direction. So therefore equilibrium shifts in which direction? In backward direction. Okay, ma? So this is the concept of effect of pressure. Now let us take one more example. Clear? For example, if I write reaction like this, so 3A to B. Now this is the reaction. Okay? So here I write pressure is increasing. Then what do you understand? So actually, if reaction should go in forward direction, that is 3A should convert into 2B, then it means the number of moles is reducing, no? Then pressure should decrease. Are you able to understand, ma? If I am traveling from 3A to 2B, that is in forward direction, number of moles are decreasing. If number of moles are decreasing, pressure should decrease. But what is the case I have taken? Pressure is increasing. It means that reaction is not in forward direction, reaction is in backward direction. So equilibrium should shift in forward direction. That's all. Okay, ma? So therefore I say reaction is in which direction? It is in backward direction. So therefore equilibrium shifts in which direction, ma? Equilibrium shifts in forward direction. Okay? Because equilibrium always shifts exactly in opposite direction, no? Whatever may be the change that is happening in 3 terms, what are they? Concentration, temperature and pressure. Then equilibrium will shift in exactly opposite direction so that that effect of change is reduced. That effect of change is nullified or cancelled, we can say. Clear? That's it. So these are the three conditions of Lechatlier'S principle. Now we will try to do some previous problems and see how questions can be asked. Okay, ma? So this is the question which is given, ma. Ammonium carbide, it splits into these products. Are you able to understand, ma? And in the process, what is happening to NH4 taken twice CO3, ma? It is increasing. Concentration is increasing. Then equilibrium should shift in which direction? Hmm? None. Oh, endukala? Very good. That is the answer. So answer is no shift. Equilibrium does not shift because this is a solid structure which we are taking. So all these equilibrium shifts, they are satisfied only for gases, ma. Are you able to understand? So here what I have taken, here I have taken a solid, no? So therefore what I write, okay, ma? No effect of change in concentration of solid. That is our answer. Okay? Okay, ma? So let us see this question, ma. 1 minute. Okay. See, ma. So this is the reaction which is happening. CH4, 2O2, CO2, and water is formed. Clear, no? And delta H is minus 170.8 kilojoules per mole. So which of the following statements is not correct? Wrong statement we are supposed to choose. Okay, ma? So first of all, let us look at the first option which is given, ma. At equilibrium, concentration of CO2 and H2O, they are not same. Is it correct? At equilibrium, he said that concentration of CO2 and H2O, they are not same. Is it correct or wrong? No. Why? Sima. So here what he is saying, for every 1 mole of CO2 which is formed, 2 moles of water will be formed. No? What is the stoichiometric coefficient of CO2? 1. Stoichiometric coefficient of water? 2. It means for 1 mole of carbon dioxide, 2 moles of water is formed. So definitely concentration of water will be greater. Okay? So concentrations, they are not same. So this statement is correct. First statement is correct. Now let us go to the second statement. So equilibrium constant, how I have to write? So the concentration of products which are in gaseous form and to the power of their stoichiometric coefficients divided by concentration of reactants in gaseous form to the power of their stoichiometric coefficients. Clear, no? So CO2 power 1, CH4 power 1, O2 power 2 should get actually. But here there is only 1 is there. So definitely this statement is wrong. So let us go for the remaining statements. Sima. Addition of CH4 or O2 will cause equilibrium to shift towards right. Is it correct or not? Huh? What is CH4 and O2? Reactants or products? Reactants. No? It means you are adding some more reactants. Okay, ma? Into the container, you are pouring some more CH4 and O2. Are you able to understand? So what happens to the concentration of reactants? Concentration of reactants will increase. If concentration of reactants will increase, how equilibrium will shift? Equilibrium will do opposite thing, no? So reaction should forward in which direction? Equilibrium should shift in which direction? Equilibrium should shift in forward direction. Then only the concentration of reactants will reduce. Are you able to understand, ma? If reaction goes in forward direction, what happens to the concentration of reactants? It will reduce. Here you are increasing the concentration, no? By adding CH4 and O2, you will increase the concentration of reactants. So more and more reaction should happen in forward direction so that the concentration of reactants reduces. So equilibrium will shift in which direction? Forward direction towards right. That is also correct. Clear, Nama? Then reaction is exothermic. What is meant by exothermic reaction? It should emit energy, no? It should emit energy. And what is meant by negative delta H? System energy is going out of the system. So correct. Are you able to understand, ma? So this statement is correct. C is also correct. D is also correct. This is the only statement which is not correct. So this is my required answer. Understood, ma? So which of the following statements is not correct, not true? So B is not correct. Okay, ma? Let us write the reasoning. So for option A, what I can write? For option A, I can write for every 1 mole of CO2 formed, okay, ma? 2 moles of H2O is formed. So definitely concentrations, they are not same. Okay? And this one here, 2 should be there, but 2 is not there. So this is wrong. Okay? And what is the reason for step number C, option number C? So if reactants are added, their concentration increases, but equilibrium will shift. Oh, but equilibrium will shift in which direction? It should shift in forward direction. Okay, ma? So that concentration of reactants decreases. Okay, because equilibrium always shifts to reduce that change, no? So reaction must proceed in the forward direction, so that concentration of the reactants reduces and concentration of products will increase. Okay, reaction is exothermic, so definitely this is an exothermic reaction. That's it.